So we're going to look at this relationship that exists between the coefficients of a polynomial and the actual roots of the polynomial themselves. So start with a quadratic. You know, if I know alpha and beta are the solutions of a quadratic, then I know it could be factorized to be x minus alpha, x minus beta. It would also have to be multiplied by a, so that when I expand it out, I'd got the ax squared. So if I do expand the right-hand side out, and then group the x's together, the other thing I've done is I've divided everything by a. Now that gets me the relationship, because remember what we said in our results, is that if the two polynomials are identical, then all the coefficients are equal. So I've made the coefficient of x squared equal, they're both 1, but I can conclude from that, well then, the coefficient of x must equal the coefficient of x. So alpha plus beta must be minus b on a. That's what we call the sum of the roots. And then alpha beta must be the same as c on a. The constant must equal the constant. And that gives us the product of the roots. And so there's the relationship that exists between our coefficients and the roots themselves. So if I now say, well, form a quadratic equation whose roots are 2 and minus 3, I can say, well, look, I know the sum of the roots are minus 1. I know the product of the roots is minus 6, and so therefore the equation is x squared plus x minus 6, or equals 0 to make it an equation, because the quadratic will be x squared minus the sum of the roots plus the product of the roots. That has an advantage when we talk about irrational roots, because a lovely thing happens there. When we add them together, the irrational part cancels out. So I get alpha plus beta is 4. And when I multiply them together, I get the difference of 2 squares. So again, the irrational bit cancels out. And we get, in this case, negative 1. So our equation would be x squared minus the sum, so minus 4x, and then plus the product, minus 1 equals 0. Sort of things they like to ask, questions we play around with. Alpha and beta are the roots of this particular equation. Now, it's not asking us to find the roots. They usually like to ask the standard one. So, okay, then what would the sum of the roots be? Well, that's minus b on a, so in this case it's 3 on 2. What would the product of the roots be? Oh, c on a, so that's minus a half. But then they like to play with the algebra. Common one we get is this one, alpha squared plus beta squared. Now it's very tempting just to say, oh well, I know what alpha plus beta is, so I'll just square it. Not quite. It's actually alpha plus beta all squared minus twice the product of the roots. Basically, I've used my perfect square expansion and just rearranged the terms to come up with a formula. So it's a handy one to remember, because as I say, that sum of the roots squared is a common sort of question they like to ask. So alpha plus beta all squared minus twice the product. We have already worked out the sum and the product, so we just substitute in what we've already found, and we end up with 13 on 4 for that one. Another common sort of question is the reciprocals of the roots. So this one I just treat like an algebraic fraction. We had a common denominator of alpha beta, and then on the top would become, well, beta plus alpha, although I've written it as alpha plus beta. Again, we've worked those two things out, so I can substitute those in, and we get minus 3. Find the value of m. This time they've told us one root is double the other. So this time, instead of calling the roots alpha and beta, I'm going to call the roots alpha and 2 alpha. So the sum of the roots will become 3 alpha, and that's going to be minus 6. And the product of the roots will become, well, that's going to be 2 alpha squared, and that's going to be m. So all right, over here I'll work out what alpha is. It's negative 2. Then I can substitute it into the other one, and we can work out what m is. So we get 8. 8 for the value of m for that one. So there's a lot of algebraic manipulation, simultaneous equations, all that sort of stuff in these sort of questions. So all right, that was a quadratic. What about other polynomials? what happens. So, as I say, in the quadratic, we just found that alpha plus beta is minus b on a, alpha beta c on a. Now with a cubic, the pattern is surprisingly similar. The sum of the roots, but now there's a third root, of course. Alpha plus beta plus gamma will still be minus b on a. So long as we always start with the leading coefficient being a and work our way down, we can use the same formula. So of course, b in this case is the coefficient of x squared, not the coefficient of x. And a is the coefficient of x cubed, not the coefficient of x squared. But if I do that, I can use the same formula. Product of the roots, well, there's actually a couple of different combinations I could have now. Because yes, there's alpha beta, but I could also have alpha gamma, and I could also have beta gamma. So the three of those will still add up to be c on a. But for a cubic, there's going to be a third one. Because if I multiply all three together, we end up with minus d on a. So there's a very nice pattern. You'll notice as we go along, it's b, it's c, then it's d. The sign alternates. So the sum with the first one is minus, then the next one's plus, then the next one's minus. So if I had a quartic, so now a is representing the coefficient of x to the power of 4. There's going to be 4 roots. All 4 of them will still be minus b on a. If I do them 2 at a time, and there's 6 different possibilities I could have there, all of those added together would be c on a. 3 at a time, there's 4 different ways I could do that. That'll be minus d on a. But now if I get all 4 of them, that'll now become e on a, and that one will be positive. To generalise that then, so as I say, if we always make a the leading coefficient and work our way down to whatever the last one would be. Shorthand notation, I can use the capital sigma to say the sum of. So the sum of the roots taken one at a time. So alpha plus beta plus gamma plus delta plus epsilon, I mean however many roots we have. That will always be minus b on a. If we were to take all the possible pairings, so we say sum of the roots taken 2 at a time, that will always be c on a. If I take them 3 at a time, that'll always be minus d on a. Did I keep going? Yes, I did. If I take them 4 at a time, that'll always be e on a. If I was to keep going, say we had a larger polynomial, 5 at a time would be minus f on a. 6 at a time would be g on a. And so on, and so on, and so on. The other lovely one is this, that sum of the roots squared, that pattern stays the same as well. So if I want the sum of the roots 1 at a time squared, it will always end up with the sum of the roots 1 at a time, square that, minus 2 times the sum of the roots 2 at a time. That will always be true. So let's have a look at a cubic. Let's do a cubic then. For some insane reason, we want to know what 4 alpha plus 4 beta plus 4 gamma minus 7 alpha beta gamma is. Alright, so first thing I'm going to do is work out the standard ones. So sum of the roots 1 at a time, that'll be minus b on a, so 5 on 2. 2 at a time, that'll be c on a, so minus 3 on 2. 3 at a time, that'll be minus d on a, so we get minus half. So there's the basic ones. I should be able to solve any possible one they want to ask me with those 3. They've asked me to 4 lots of alpha plus beta plus gamma, so that's 4 lots of 5 on 2, minus 7 lots of alpha beta gamma, so 7 lots of minus a half, which is 27 on 2. The reciprocals for this one, well again, I'll treat it like an algebraic fraction. Common denominator, alpha beta gamma. On the top, we end up with beta gamma plus alpha beta. Well, that's the sum of the roots 2 at a time. So we've worked that out. We've worked the denominator out as well. So we get minus 3 on 2 on minus a half, which is positive 3. That negative's not there, okay? Just, you can't see the negative. It's not there. I see, told you it's not there. Where'd it go? Alright, so it should be positive 3, of course. Alpha squared plus beta squared plus gamma squared. I said that's always going to be the sum of the roots 1 at a time squared minus 2 times the sum of the roots 2 at a time. So let's substitute that in. We'll get 5 on 2 squared minus 2 times minus 3 on 2. That one turns out to be 37 on 4. So just like the quadratic, it's once you've got the 3 basic ones, it's usually a lot of algebraic manipulation and substitution to come up with your final answer. Let's have a look at a very old HSC question. So we've got a cubic. They want us to find alpha plus beta plus gamma, say a basic one. But this was a little bit tricky, this one. I don't know if you see or can work out what the common mistake would have been for this. The answer is actually 0. What do you reckon a lot of people put down as the answer? Three, yeah, because they've just gone, minus b on a. They've seen, -3, that's the first number there. So we'll put that in. But remember, no, it's the coefficient of x squared, which in this case is 0. So the sum of the roots 1 at a time would be 0. Next one, they said they wanted the product of all 3. So in this case, that would work out to be -1. Then they asked for the reciprocal ones. These are all very standard ones that they ask, a lot of them. So we'll treat it like an algebraic fraction. 2 at a time. We haven't worked that one out yet. But 2 at a time would end up being -3. Oh no, here we go again. -3 divided by -1. Come on, 3. Come on, 3. +3 for that one. +3. A little bit more recent. It's known that 2 of the roots are reciprocals of each other. They're reciprocals. So in that case, instead of calling the roots alpha, beta, and gamma, I'm going to call the roots alpha, 1 on alpha, because it's the reciprocal, and I'll call the third one beta. Now, what can we do with that? We've got to find k. Well, I'm going to do product of the roots first, because the nice thing about reciprocals is when you multiply them together, you get 1. So I can actually get an answer for beta straight away with this one. So I get the beta is -3. Now, the way I'm going to do this one now is use my factor theorem. Because I now know that -3 is a root. Therefore, when I substitute in -3, I'll get the answer 0. And so I just have to solve that one now for k. And we get, eventually, 13. Now, of course, you could have played around with some of the roots 1 at a time, some of the roots 2 at a time, created simultaneous equations, and you would have got k as well. But I just took advantage of what else we know there to do it a little bit quicker. 2006 paper. Oh, no numbers this time. Okay. Polynomial x is x cubed plus rx squared plus sx plus t. And all we know about rs and t is that they're real. And it's told us that the solutions, or the zeros, are 1, alpha, and -alpha. We've got to find out what r is. Well, r's with the x squared, so it probably makes sense to do some of the roots 1 at a time to come up with an equation with r. Oh, look at that. It actually drops out quite nicely. Because one's the negative of the other, the alpha and the minus alpha cancel in this one. And we get r is -1. Find the value of s plus t. So I've done 2 at a time. So 1 times alpha plus 1 times minus alpha plus alpha times minus alpha, that's going to be s. So s is minus alpha squared. If I do 3 at a time, I get 1 times alpha times minus alpha. So that gives me t is alpha squared. Well, s plus t then is 0. So the other way, as I could have done it, is I said, well, we know 1's a solution, so polynomial 1 is equal to 0. So 1 plus r plus s plus t is equal to 0. We just worked out in part I that r is -1. So sub that in, and we get s plus t equals 0. A couple of ways we could do that particular problem. Okay, so 10F we shall add to our list of questions.